G'day ladies and gentlemen, it is the Raging Ranger here. Who else would it be? No one else is smart enough to do this stuff. Well, not yet anyway. That's the point of this video. Welcome back to our topic on derivatives. And this time we're going to be talking about stationary points. So a stationary point of a function is anywhere where f-x, the slope function, equals 0. So if you think about it, it's almost like a roller coaster. Here's our roller coaster there, our stationary point. So you go on up the roller coaster, starting down here. So here's a stationary point right down the very bottom where it's horizontal. You're going up, get to the very top, and you're stationary right there. And then you go, and here's another stationary point down the bottom. It's anywhere where your slope is 0. So it will either be a local maximum. So here's a local maximum point. It's the highest point on this graph. Or a local minimum. So the lowest point on a graph in that particular area. Or else it can be a little bit funky and be an inflection point where the graph has gone from being negatively shaped to positively shaped. So it's that point where it's just gone flat. And that's what we call a stationary inflection, because a stationary inflection is a type of inflection where it does actually level out to a horizontal there. Notice that this is a local maximum because there are some higher values over here, but in the immediate vicinity, it's a high point. And not all graphs will have just one maximum. Some graphs might have just one maximum or one minimum. It might not have a minimum. It might only have a maximum or vice versa. It might not have an inflection point. But all of these things will have a derivative value of 0. And this is very useful stuff for when we're looking at real life applications, because we can start applying this to optimization. What is the maximum amount of money that could be made off of a certain method? What's the minimum amount of material to build a certain fence with a certain area? What's the point where we've gone from a decline in profit rate to an increase in profit rate? So this is all the stuff that this can be used for, which we'll be getting to very soon, I assure you. So previously we looked at sine diagrams, and here's what you'll notice about stationary points on sine diagrams. So when we have a stationary point that is a local maximum, your sine diagram will go from going positive till it gets to point A. Point A is our stationary point, and then after point A, our graph is negative. It's going down like that. On the other hand, and that's what the shape of the curve would look like near that point. Local minimum, opposite. It's been all downhill, negative. Then after A, it starts going positive again. But directly at A, so f dash A will equal 0. So just at A, we're going to get a flat point, a horizontal point, or a horizontal slope, I should say. And the graph would look like that. So the shape of that f of x curve would look like this at that point. Stationary inflection, well, it depends what the inflection looks like. So here, if we're going positive, it flattens out at A, but then it keeps going positive. It's still happy. It's still an upwards increase. It's still an upwards increase. Whereas here, we're going negative. So it's a decreasing slope, and then it's negative here as well. And that corresponds to this kind of shape. So definitely draw down this green table, because that will give you an idea of a visualization of what the sign diagrams are doing and the graph is doing around a local maximum, minimum, and stationary inflection point. And it then becomes desirable to find the values of x, so to find this value a, at a local maximum for a certain graph. So to find the stationary points of a function f of x, we find the values of x where f dash x equals 0. So if you've got some f of x and you want to find its stationary points, first step, find f dash x. Second step, find x where f dash x equals 0. So that's exactly what they're doing in example 12. Let's have a run through this now. Shall we? I think we shall. So we want to find and classify all the stationary points. For f of x equals x cubed, take 3x squared, take 9x plus 5. So we're going to be using a few different tools here. First things first, we need to differentiate this function. So to do that, apply your rules and you're going to get this. Remember, there's only 3 terms here now because the 5 drops off. Derivative of a constant is 0. There's your derivative function, f dash x. If you're unsure of how to get that derivative video, then you're not If you're unsure of how to get the derivative, then you're not watching my previous videos. Go and watch them, and then like and subscribe, and give me your money. Alright, so there's our f dash x. Let's get that into a bit more usable form. So the whole point of this is that we've got our f dash x now. That was our first step. Second step is to find all the values of x when f dash x equals 0. So essentially what we're doing is 3x squared, take 6x, take 9 equals 0, and solving for x. Let's calculate the values of x that satisfy this equation. Now there are lots of different ways that you can do this, and you've seen those probably in previous videos. If not, get good. What are you doing over here? And the version they're using here is factorizing. They factorize out 3, so the common constant factor. Then they factorize x squared take 2x take 3 down to x take 3 times x plus 1. You could also use quadratic equation. You could use completing the square. You can use any number of methods. But basically, the bottom line is you can even use your graphics calculator to solve it all for you. Why not? We live in that kind of day and age. Either way, we find that when this function here equals 0, so the slope function equals 0, we get x is 3 or negative 1. So that means we're going to have 2 stationary points. 2 stationary points at 3, so a stationary point at 3 and a stationary point at negative 1. Now, if we want to know what kind of points they are, you might want to draw this graph on your calculator or draw a sign diagram. Personally, I'm going to use a calculator because, as a famous, wise African-American woman once said, ain't nobody got time for that. So here's my calculator. I'm going to draw a graph of y equals, where are we? 3x squared, 3x squared plus, no, not plus, take 6x, take 9, and we're going to draw that graph, and we get something that looks a bit like that. Let's zoom out, auto, it's still not quite good enough. We're going to need a on up. No, that's good for us. That's good. Because what we want are that point there. Oi, go away. We want that point there and that point there. So to do that, let's go gsolve. Let's go x calculate when y equals 0. X is going to be -1. Let's scroll across the other point and 3. There are our 2 points there. So you can use your graphics calculator for that. And what kind of inflection points they are, well, we need to draw the original graph. So rather than 3x squared, yada, 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 we need x cubed take 3x squared take 9x plus 5. Going to draw that graph. And bingo bango, let's zoom that out auto. There we go. We have our first point, stationary point, and that is a local maximum. And we have our other stationary point here at 3, which is a local minimum. You can actually find these points directly off of this graph using your calculator, FYI. Gsolve, max, right there, -1. Gsolve, minimum, right there, at x equals 3. How easy is that? And it also gives the y value. How easy is that? And it tells you it's a minimum as well. So if you've got a Casio, then you can do that pretty easily. If you've got a Texas Instruments, yeah, well, have fun with that. It's not great. So find the greatest and least value of y equals x cubed take 6x squared plus 5 for this particular interval. So to do that, you can do exactly the same thing. Draw the graph or use the same process as we were describing before. So using the conventional method, let's start by getting the derivative. So to get the derivative of y equals x cubed take 6x squared plus 5, we're going to get that and that. And when the derivative equals 0, you can calculate the x values however you normally do it. You're going to get x is 0 or 4. Sure enough, here's a graph of our original function. And at 0, you can see there's a maximum. And at 4, you can see there's a minimum. So that means that the greatest value in the interval -2 to +5 is at x equals 1. So you need to plug x equals 1 back into your equation here. And you will get 5. Y is 5. And you'll also get, if you plug 4 back into your original equation here, you'll get a y value of -27. The other critical values are the endpoint here and our endpoint here. And you could see it could have been the endpoint on the extremes that was the lowest value. So that could have been the lowest value. It didn't necessarily have to be that minimum that was the lowest value within that interval, but it just so happened that for the values they gave you for the interval -2 up to 5, the minimum was still sort of the lowest point. So in fact, the minimum and the end point there, the leftmost point, were the minimum values. Now, if you notice, if this had been any smaller, so if that had been -3, then the leftmost endpoint would have been the least value on that graph. It would have no longer been the minimum, because we're no longer just talking about a local minimum, we're talking about the minimum over an entire range of values. So just something to notice there. And that's it for this section, ladies and gentlemen. Give these questions a go, and until next time, stay classy.